Welcome to 5.2. We are going to do function composition today. The last lesson we did was function operations, where we took two functions and added them together or subtracted them or multiplied or divided. Today, though, we're doing composition, which combines two functions but in a slightly different way. We're going to look at it in a table form, like for single values, how do you evaluate composition? Then, just like we did with our function operations, we're going to look at how to write a completely new function that kind of does the job for you, right, in one step. Like rather than having to do each one in two steps, we're going to reduce it to one step. Then we're going to talk about determining the domain and range of your composition of two functions. So let's get right into it. Here I have two functions. F of x is negative x plus 8, and g of x is 2x squared plus x. And we're going to use function composition. Now the way operations worked, we took an x value, we stuck it into f, we stuck it into g, we got both answers, and then we added or subtracted or multiplied as appropriate. In function composition, you don't stick x into both functions. We're going to take the x value and stick it into the first function, and then we take the answer from that function to stick into the other function. So I'm going to take this 2, I'm not going to stick it into g, I'm going to stick the 2 into f. Negative 2 plus 8 is 6. And so what I stick into g is 6. I'm going to take the answer to f and stick that into g. This is the way I like to write function composition because it gives you a picture of who's on the inside and who's on the outside. Although the traditional way to write this is with the little open circle, g of f of x. Make sure you do that right to left. You take x and you stick it into f, and then you take f and stick it into g. Which really is the way that we do our functions. We take this number on the right and we stick it into the function. So it's an extension of that. But I take the 2, I stick it into f, I get 6. So this is g of 6. If I stick 6 in here, I get 2 times 36, which is 72, plus 6 is 78. And if I stick in 3 to f, I get 5. G of 5 is 2 times 25, which is 55. If I stick 4 in here, I get negative 4 plus 8 is 4. G of 4 is 2 times 16, which is 32, plus 4 is 38. And if I stick 0 into f, I get 8. And g of 8 is 64 times 2 is 128, plus 8 is 136. So that's composition. You take the number, you stick it into the function on the right, or the inside function, get the answer to that, and the answer is what you stick into the other function. We can flip this the other way around. We can do g of f of x, which means we take our x values and we stick them. Oh, I wrote the same thing. F of g of x, f of g of x. If we do f of g of x, we take x, we stick it into g, we get the answer, and stick that into f. So I'll start with 0. If I stick 0 into g, I get 2 times 0 plus 0, which is 0. I stick 0 into f, I get 8. If I stick 1 into g, I get 2 times 1 plus 2, which is 4. If I stick 4 into f, I get 4. I'll do 2. So if I stick 2 into g, I get 8 plus 2 is 10. And if I stick that into f, I get negative 2. So here, point by point, you just stick it into the first one, but you take the answer to that to stick it in the second one. You don't stick x into both of them. As indicated, this is 2a. As indicated, I'm now going to show you how to write a single function for this. If you're doing g of f of x, what you want to remember is that this is not actually new. In chapter, I think it was in chapter 4. Chapter 4, we talked about function notation and how we use it. I can stick a 2 into g, and that would be 2 times 2 squared plus 2. I can also stick, say, an a in there, and that would be 2 times a squared plus a. So all that's really happening now is I'm sticking f of x in there, which is going to give me 2 times f of x squared plus f of x. It's not different from what we did before. It is more complicated, though, because f of x is negative x plus 8. So negative 2 times negative x plus 8 squared plus negative x plus 8. If I expand that square, that's x squared. It'll be negative 8 times 2, which is negative 16x, and 64 times 2 plus negative x plus 8. So that's 2x squared minus 32x plus 128 minus x plus 8, or 2x squared minus 33x plus 136. Which will give me these answers. If I stick 2 in here, that's 2 times 4, which is 8, minus 66 plus 136. 136 and negative 66 makes 70, plus 8 is 78. So it's one function that does both steps at once. I can do it the other way around. F of x is negative x plus 8. So f of g of x is negative g of x plus 8, which is negative 2x squared plus x plus 8, or negative 2x squared minus x plus 8. So I can combine them singly, like in a table, and I can also combine the equations to get a new function that handles my composition for me. Now I have to find my paper. All right, so there's another way that this happens in your book. We can actually define our functions by points, which we've done before, although not since chapter 2. But we're going to do an example now where f and g are defined by a series of points. And so I don't know, it's not really more complicated, but it might feel a little different, so I figured I'd better do an example. Now I'm going to take, first I'm going to do f of g of x. So the first thing I'm doing is taking x values and sticking them into g. So I'm going to start with 7. If I stick 7 into g, the answer should be 0. Right, that's how these points work. You're sticking in the ones on the left, you're getting out the ones on the right. So if I stick 7 into g, I get the answer 0. If I stick 0 into, I take the answer, right, to g, I stick that into f. So this is f of 0, which is negative 1. So if I stick 7 into f of g of x, I get negative 1. Or if you prefer, f of g of 7 equals negative 1, or f of g of 7 equals negative 1. Similarly, I can stick in negative 1. I stick negative 1 into g, I get 7. I stick 7 into f, and I get 7. So f of g of negative 1 is 7. If I stick in 4 into g, I'll get 9. Stick 9 into f, I'll get 4. If I stick, lastly, 8 into g, I'll get 2. If I stick 2 into f, I get 6. So f of g of x. Now, this function g is only defined at these 4 points, which means if we need to write the entire equation for f, or the entire relation for f of g of x, we can do that. Well, not f of g of x, but f of g anyway. We can stick it in there, and we just have to include our new points. 7, negative 1, negative 1, 7, 4, 4, and 8, 6. Now I'm going to do that the other way around. I'm going to do g of f of x. So I'm taking my values now and I'm sticking in f first, and then take the answer to that to stick into G. So the first thing I'm going to do is try 2 x f g of f. So when I stick 2 in there, I get 6 from f, but there is no 6 that I can stick into G. So we're undefined over here. Undefined. I'm not allowed to do that. It doesn't work. So that point, I'm never going to get to use. I can't use that in G of f because it breaks in the middle. There is no value for G where I can stick in 6. That one's broken. But I can try 9. I get 4 from f. If I stick that into G, I get 9. So that works. I can try 7. If I stick 7 into f, I get 7 out of f, which if I stick that into G, I get 0. And I can stick in 0, which f gives me -1, to which G gives me 7. So G of f is 9, 9, 7, 0, and 0, 7. It's only got 3 points because 2, 6 didn't work. I couldn't stick the 6 in. Also, this 8, 2, there's no answer for f that gives me 8. So this point never gets used either. And this is what brings us back around to our third point. Identify the domain and range of your new function. When I do f of g, my domain is the x values that are acceptable to use. -1, 4, 7, and 8, which I put in ascending order, although that's technically not required. So if you don't put them in ascending order, I can't mark it wrong. The range is the y values, -1, 4, 6, and 7. But in G of f, I never get to stick in the 2, and I'll never get 2 as an answer for G of f because they don't line up right. So the domain here has only 3 parts in it. 0, 7, 9. And the range is only 0. Oh, it's also 0, 7, and 9. Interesting. When you're doing domain and range from an equation, if the inside function has numbers you're not allowed to stick in, you have to indicate that for your domain. But polynomials, the domains are all real numbers. So all of the domains for our compositions today are going to be all real numbers. The only problem is the range won't be all real numbers, but you can use Desmos to find the range for any of these. Like this is a quadratic, it's a parabola, so it's going to have a minimum value, and all you have to do is find the minimum value. This particular one I graphed on Desmos earlier and found that its minimum was at 8.25, -0.125. I just pulled that off of Desmos, which means for G of f of x, my domain is going to be all real numbers, and my range is going to be y is greater than or equal to -0.125, because that's a parabola that opens up. It has a minimum value. When I do f of g of x, I'm going to look here. You can look on Desmos. I did this one earlier as well. You can also, use the opposite of b over 2a to find the vertex. You can. Let's see, that'll be +1 over -4. I kind of doubt any of you will bother because a lot of these are going to be fractions. So if I stick -1/4 in there, I get -2 times 1/16 plus 1/4 plus 8, which is -1/8. 1/4 is 2/8, and 8 is 64/8, so that's 65/8. This one opens down because it's got a -a, so its range is y is less than or equal to 65/8. Well, like I said, you could have gotten that 8.125 from Desmos. Domain is all real numbers. All the domains are going to be all real numbers for this one. Oh, I'm out of time. But it's okay because I finished my lesson. Uh, I have posted the assignment already in Google Classroom, to which you found this video attached. But in case you didn't see it, 5.2 starts on page 325, and we are doing 16 through 56, only the multiples of 4. So you only have to do every fourth problem. Good luck, and let me know if you have questions.